Today's lesson is on CSEC Industrial Education. We will be focusing on CSEC and Cape Electrical. I am Devalian Green and
I am Sean Myers. Now today, ladies and gentlemen, our topic is inductors and inductance. Now our objectives are inductors and the types of inductors that we have. We're going to be focusing on inductors in series as well as inductors in parallel. And we're going to be looking at factors that affects inductance and how we can derive some formulas from that, as well as the principles of inductive circuits. We're also going to be looking at the rise of current in inductive circuit. Now this is where you'd actually hear people speaking about, growth and decay curves. And finally, we're going to be topping it off with energy stored in the magnetic field of an inductor. Now I'm going to be handing over to Mr. Green, and Mr. Green is going to be taking us now through inductors and inductors.
all right. So as stated by my colleague, we're looking at inductors and inductance. So before we can get deep within the content, we must understand what an inductor is. And if you'll just point your attention to the slide that we have here. All right. An inductor is a passive two-terminal element designed to store energy, right, in its magnetic field. All right. An inductor is also called a reactor or a coil. We can even go further to break that down to say that an inductor is a coil wound around a core that possesses a large value of inductance. And here we have with us some real-time samples of inductors. Here we have a coil that was removed from the circuit board and one that is still attached. All right? Now we're going to be talking about the types of inductors. All right? Now there are two main categories of inductors. We have what we call the air core inductor, and we have the ferromagnetic core inductor. Right? Ferromagnetic core is mostly made up of iron, right? And the air core, as its name suggests, is air, right? Now, inductors normally have a standard or steady value of inductance, but we also have what we call variable inductors. Now, you may be wondering, right? Why are inductors important? Where are they used? Inductors are basically, they provide what we call a resistance to the change of flow in current. And this characteristic of inductors is very important when we look at rectifier circuits, right? And inductors are found commonly in day-to-day devices. So if you check your televisions, your radios, you can find inductors paired with capacitors. All right.
And, to add a little bit to that as well, as was mentioned earlier, that an inductor provides an opposition to a change in current. Now, our students out there, of course, you'd have already had prior knowledge pertaining to resistors. Yes. And you know that resistors opposes the movement of electrons. But you're now learning about inductors, and inductors, it offers opposition, but not in the form of a resistor. But this type of opposition is actually to the change in the movement of electrons. Right. Now, if we think about a door, if, all of us have doors. Now, if you have a door for your house, the front door for your house, then of course, if all students were going to be lining and going through that door, we would say, all right, come in single file. So that means that it's going to be a person going through the door. Now, when you think about that illustration, then it is very easy to understand that the door will serve, will be opposing your movement. But think about an inductor. An inductor opposes the change. So if you're coming in single file, then it will allow you to come in single file. But what the inductor will oppose, on the other hand, is if you should choose to come in pairs, or you should choose to come in groups of 3s or 4s. It will oppose the change while on the other hand, the resistor just opposes, the movement of electrons, so to speak. So we really hope that you understand that definition very clearly because it is very imperative in your upcoming exams.
All right. Thank you, Mr. Myers. Now, moving on. We just discussed the principle or concept of inductors, right? Now we want to know specifically what is inductance. And inductance, simply put, is the opposition to the change of flow of current, right? Now, there are two main ways in which induction takes place. And as you can see on our slide here, the first method is known as self-induction. I'm just going to read what we have here. Now, if changing current flowing through a coil produces an EMF or an electromotive force in the same coil, it is called self-induction. And just to clarify or explain what that is saying, basically that principle is based upon current flowing through a coil will generate what we call a magnetic field. Once this magnetic field comes in contact with the coil or cuts across the conducting wires, it will generate or induce a voltage within the coil, and that is known as self-induction. All right? Our second method is known as mutual induction. Now, once you hear the term mutual, you know that this is taking place between two or more parties right off the bat, right? So now we have here the changing current flowing through one coil will produce an EMF in another coil, and this is called mutual induction. So basically what we're saying is that if we have two inductors in close proximity to each other, the magnetic field of the neighboring inductor will induce a voltage in the other. All right? And that is what we call mutual induction. All right? Hope you're paying attention. Moving on. All right. We want to look at how inductors operate in simple circuits. All right? And if you have an electrical background, I know you will know how we calculate resistors in series and resistors in parallel. Now, I'd just like to point your attention and let you know that inductors operate basically the same way as a resistor in series or a resistor in parallel. And from that, we can go ahead and derive our formula that the total inductance, or LT, is equal to the sum of the inductors within the circuit. So here we would have the formula LT equals L1 plus L2 plus L3. And you can have a varying amount of inductors within a circuit. The formula doesn't change. So if you have 4 inductors, you know you'd have L1 plus L2 plus L3 plus L4, and so on and so forth.
All right.
All right.
So now what we're going to be looking at is the said circuit here that we have on our PowerPoint. We're going to be looking at that circuit on our board. So as you would have observed from the slide, that L1 is 10 henries, L2 is 20 henries, and L3 is 30 henries. Now, of course, you would have derived from this that the unit for inductance is actually the what? The Henry. And its symbol is a capital H. Very important, students, that you pay attention to that. Now, as Mr. Green mentioned earlier, that LT would be equal to L1 plus L2 plus L3. And it doesn't matter any amount of inductors you have. It could carry on until you have even, 1,000 inductors. To find the total inductance, you simply are going to be carrying out, using this formula by adding them. So in working it out, L1 equal to LT equal to L1 plus L2 plus L3. It's very important that you start with your formula. And then from there, you're going to have your 10 Henry plus 20 Henry plus 30 Henry. And then from doing that now, you'll realize that you'd have a total of 60 Henry. So that is how you actually carry out, performing calculations for inductors connected in series.
Brilliant. All right. So as we mentioned earlier, inductors in series operate similar to those of resistors in series, and it's the same for inductors in parallel. Now, if we were to look at our PowerPoint right here, we can derive our formula. LT would equal to 1 upon the value of L1 plus 1 upon the value of L2 plus 1 upon the value of L3. And just as we mentioned with the series, inductors in series, you can have a varying amount of inductors within any given circuit. So you would continue using this formula just the same to suit the circuit, right? And we're just going to be putting one of these examples on the board for you real quick.
All right. Now this is now going to be an example of an inductor in parallel. Now, how do we know that this is actually a parallel circuit? Well, for those who are at home, I hope you answered correctly. So a parallel circuit, it provides multiple pathways for current to flow. So if we had IT leaving the source here, IT, then of course this current will actually split into one, I1, it will actually split into two, I2, and then it will actually split there, I3. So you'll have actually three currents that are going to be, coming from IT. And as these currents flow, then of course IT would come back to its source. So these three currents again will be added, giving you back the total current. Now, let us just use a simple example. Let us say that this is 1 Henry, this is actually 2 Henries, and this is actually 3 Henries. Now we are going to be asked to calculate, our total inductance. Now the formula, if you look at 1 over LT, which is equal to 1 over L1 plus 1 over L2 plus 1 over L3, and this could carry on to any number of L, 1 over Ln. Now we're going to be inserting our values in our formula. So 1 over LT would equal to 1 over 1 plus 1 over 2 plus 1 over 3. Now we find our LCM. And what do you think our LCM will be for that, students? Now if you're guessing the number 6, then certainly you are correct. Right. So in reducing this now, 1 into 6 goes, nice, 6 times. 2 into 6 goes 3 times, and 3 into 6 goes 2 times. Now if we add all of these, 6 plus 3 plus 2, we would have 11 over 6. So 1 over LT would be equal to 11 over 6. But bear in mind, students, that what we're trying to find here is actually what? LT.
Yes.
Now 1 over LT is not LT. So we need to find the reciprocal of this. Now the reciprocal of this, LT, would be equal to, this will be 6 over 11. And if you're using your calculator, that will be 0.5 Henries. Now, it is very important to pay attention to this as well, that for inductors in parallel, the total value of the inductance in parallel will always be less than the smallest value inductor in the circuit. So the smallest value inductor in the circuit is actually 1 Henry. But when you calculate, you realize that the total inductance is actually 0.5 Henries, highlighting, that your answer is in line with what we're looking for.
All right. Now we're going to be directing your attention to our next objective, which has to do with the factors affecting inductance. Now, the first factor that affects inductance is the number of turns of a coil, right? So that would have to do, like bringing back to our depiction of the inductor, you see that it is made up of a number of turns of the coil, right? Now, depending on the amount of turns around the core, that directly impacts the value of inductance produced by the coil. All right, our second factor is the diameter of the cross-sectional area of the coil. And when we say the diameter of the cross-sectional area, we are mentioning or we are referring to the thickness of the material used for the coil itself. All right? Thirdly, the length of the coil. Now, if we were to go ahead and unwind the coil that makes up the inductor, we would then be able to see the true length of the coil, right? And this dimension or this distance also impacts the amount of inductance produced by a given inductor. The final factor, the permeability of the core material. All right? Now, when we mention permeability, what we are referring to is the ability of a material to promote the magnetic lines of force. All right? So, in other words, or in essence, it can be linked to conduction, right? So, how a material would conduct electricity, but in this sense, we're speaking to magnetism. All right? Good. Now, based on what we just derived, we can go ahead and use our formula on the board, which is L, which in this sense is induction or inductance, is equal to N, which is the number of turns of the coil, times phi, which refers to the magnetic lines of force, divided by the current, which is produced by the inductor. That will give you the value of inductance of any given inductor. All right? Also, we can transpose for mu, right? And this is the permeability of the core material multiplied by capital A, which is the cross-sectional area of the coil itself, times N squared, number of turns, divided by the length of the coil. And these two formulas will go ahead and give you the value of inductance of any given inductor. All right?
I can also add something there, Mr. Green. That we have a lot of students at home right now. Some students, they're in grade 10, some are in grade 11, some are in grade 12, and you have students as well who are in universities pursuing career along this path. Now, based on what we have discussed so far, you realize that it is applicable to all, but it is actually now based on your level. Questions will be derived or, come up with based on your level. Now, if you think about it, if we should just put back a simple series circuit with inductors on the board, we have two inductors in this circuit. These are two inductors, L1, L2. Now, CSEC could simply say to students in grade 10 and 11 that, okay, this is 5 Henry, and this is actually 3 Henry. So you know that the total inductance, based on what we would have stated earlier, would actually come up to being 8 Henrys. But for those who are in grade 12, now this is where things get a little bit interesting. Because CSEC will say to you that, look here, this is 5 Henry, but when it comes to this inductor right here, the permeability of the core material is XYZ. The cross-sectional area is whatever meters squared. Its number of turns is, and the length of the conductor. So now you would have to know this formula to come up with the what? The inductance for that particular inductor. And then now from there, you'll be able now to resolve, the circuit.
All right. Now we're going to be looking at inductive circuits, the opposition to the change in current.
Yes, sir.
All right.
All right. So now we're going to be taking over from Mr. Green right here. And, in talking about inductive circuits, of course, as we mentioned earlier, that inductive circuits refers to the what? The opposition to a change in current. Now, there are certain principles for us to understand. A current-carrying conductor develops a magnetic field. Now, if the field is changing, ladies and gentlemen, then one thing that we can assume is that the current is also changing. Now, a changing field is referred to as a moving field. That simply means that the field will either be expanding or collapsing. Now, another principle for us to pay attention to, And this is where the electromagnetic induction comes from. If there's relative motion between a conductor or coil and the magnetic field, then a voltage is induced in the conductor or coil. Now, let us look at what we're saying here. This is an example. Let us say that this is a conductor or a coil. And if there's relative motion, as was stated earlier, then, what is going to happen is that you're going to have induction taking place. A current will be induced in the conductor or coil. Now, based on that, we are going to come up with, there's a law that speaks to that. And that law, ladies and gentlemen, is Lenz's law. So that is what we're having right here on our screen, Lenz's law. Now, Lenz's law speaks to the direction of that induced EMF. Is always such that it tends to set up a current opposing the motion of the charge of flux. Now, if we look at the board, and let us see if we can actually clean off the board. And we're going to take it to the board shortly. Now, when we talk about Lenz's law, sometimes in Jamaica we think about a bad mind thing taking place. Lenz's law speaks to that. We're going to be talking about an applied current, and we're going to be talking about an induced current. Now, what causes the induced current is a good question. Well, you will realize that the induced current is as a result of the applied current. The induced current is as a result of the applied current. But instead of the induced current supporting the applied current, you know what it does? It fights against it. It opposes it. And that's a bad mind effect. So anytime you think about Lenz's law, always remember that. That bad mind thing that takes place. So let us look now at our board. And Mr. Green is nicely drawing that lovely circuit for us on, the board. Now, in speaking about this circuit, 1 minute there, Mr. Green. So in speaking about this circuit, all right, let me just take over from here, Mr. Green. So this circuit here, let us say we have a supply voltage. Now, this supply voltage, as a result of it, we're going to have our applied. This is the current that results as a result of our applied, as a result of our supplied voltage. Now, this applied voltage, it comes and it flows through our coil that is right here. And as a result of this applied voltage, then, as was stated earlier, that this coil is going to develop a what? A magnetic field around it. And because of that magnetic field, then an I induce will be developed. That is our induced current. But this induced current, it will not flow in the same direction as our applied. But what it will do is that it will oppose our applied. So that is where Mr. Green has this formula that IT would actually be equal to I applied minus or what? I induce, opposing. And that is what Lenz's law actually speaks to. Now, it is very important that we understand this clearly. Very important. Because where we're going to be heading in terms of, the rise of current in inductive circuits, then, this Lenz's law is going to be coming back to the fore. Now, if we should look at the rise of current in inductive circuits now, then let us look at a circuit quickly on the board. And for this circuit, we're just going to add a resistor. So we're just going to add a resistor to this circuit. So let us just add a resistor to this circuit. So this is our R, and of course this is our inductor L. Now we're going to be putting a little switch in our circuit as well, because we want to have a little control mechanism. So let us say that the switch is closed. Now when the switch is closed, then you notice that there are a few things that will be happening. For one, the current that is flowing through the inductor will be rising. That is one important thing. The current that is flowing through the inductor, it will be rising. Now, we could easily do a little graph, because all of this is happening with respect to time. All of this is happening with respect to time. So if we look at, I, which is our current, this could be our I applied. So if that is our I applied, then we could also say that this is also represent our IR because it's a series circuit. So this current will be rising, and it will be rising exponentially. Very important that we bear that in mind. It will be rising exponentially. Now the next thing again is that the voltage drop across our inductor, it will be falling. It will be falling. Now if we should represent this on our graph, then certainly, well, we could get a new graph. We have a little space right here. So we could say that this is VL. Now VL will be falling, but you notice it is falling exponentially. So these are not linear graphs, students. These are exponential graphs. And then now based on the level that you're at, like for example the grade 12s and those in universities, then you will be doing a lot of graphs pertaining to these. And you'll be working on the year under the graph and using your mathematical principles and so forth to come up with a lot of the solutions to the questions that will be asked. So this is we're trying to help you to appreciate the principle though, that VL will be falling, the inductor voltage, but when it comes to the applied current, or the current that is flowing through the inductor, which will be the same current that eventually will be flowing through the resistor, then that current will be rising. So those are some important things to pay attention to. But one important point to note is that when we have maximum current flowing, then this inductor, it no longer has an effect on the circuit. Now we can illustrate this, and we can think about you having a hose at your home. And of course that hose might be wrapped up around something that you use it to store. Now you come and you turn on the pipe at full pressure, the water pipe at full pressure. Now when you turn on the water pipe at full pressure, then let us pay attention to what is going to be taking place. Now the first thing that you will observe is that water will be coming through the pipe. Now that water that is flowing through the pipe could be referred to as your current. The current flows through the circuit. But remember, you know, that just like this coil of wire that we have right here, the hose is wrapped up. So at t equals 0 second, and you look at the end of the hose, you realize that there is no water that is coming. But as time starts to pass, you realize that the water is gradually, the pressure of the water is gradually increasing until, probably after a few seconds, you realize that all of that wrapped hose, it no longer has an effect on it. Because guess what happened? The water is now coming at normal pressure. So whether you length out the hose or not, the water is coming at normal pressure. So this is what we're stating, students, that once you have maximum current flowing through the circuit, then the inductor no longer has an effect on the circuit. It now boils down to you just having a resistor in the circuit. So we're going to be looking at the rise of current in inductive circuits. Now these are the facts. Number one, it is very important that you pay attention to this. It takes 5 time constants for current or voltage to rise to maximum or fall to 0. So how long? 5. Remember we were talking a little bit earlier about the hose. So how long would it take for that water pressure to be steady? 5 time constant. Now a time constant for an inductive circuit is actually tau would be equal to L over R. It is very important that you write this down in your books and you have it ready because we're going to be working out a circuit together. Now as we look on, there are 2 factors that it is very important that you pay attention to as well. One is referred to as the rising factor, and the other is the falling factor. Now let us look at our rising factor firstly. Our rising factor is 1 minus e to the minus t upon tau. And then our falling factor, and we're going to be using a different color. So our falling factor is actually e to the minus t upon tau. So as was mentioned earlier, notice that these are not linear graphs. These are exponential graphs, and that's the reason why you have, your exponential icon right there. So these are found, ladies and gentlemen, on your calculator. It's very important that you get used to it. Now, as we highlighted to you, our rising factor and our falling factor, now what we're going to be looking at now is our circuit. And let us see if we can understand now how we can go about using these 2 factors in making some calculations. Now, if you look at their circuit, if you look together at your circuit now, you realize here that your circuit, it has a 100 millihenry inductor in it, and it also has a 20 kilo ohm resistor in it. And your voltage supply is actually 20 volts. Now, let us see who can actually work out the circuit, work out their circuit, and actually come up with the correct time constant. I'm going to give you like around 10 seconds to do that while I raise the board and see if I can also put, you know, my time constant on the board as well. So, Mr. Green, can just clean off. All right. So I hope you're coming up with it, students. So remember the formula that you're using. So for your time constant, tau is equal to L over R. All right. Now, let us look at our board together now. So your time constant tau is equal to L over R. All right. Now, what is your L? Your L is equal to what? 100 millihenry. And your R over R, which is what? 20 kilo ohm. Now, you know that milli is times 10 to the negative 3 Henry over R, which is what? 20 times 10 to the 3 ohm. Now, when you calculate all of that, students, what did you get for your answer? Well, 5 times 10 to the negative 6 seconds. Or, if you want to use your units, it will be 5 microseconds. All right? So that is what we receive for our what? Our time constant. Our time constant for this circuit is actually 5 microseconds. Now, what if we were asked, you know, what is happening at 15 microseconds? But before we move on to 15 microseconds, remember we mentioned, you know, that it takes 5 time constant for the current to rise to its maximum or fall to 0. Now, that is very important because, you know, if we should calculate for this circuit, for it to reach a maximum, then it is 5 time constant, 5 tau. So maximum is equal to 5 tau. So 5 times 5 microseconds equal to what? 25 microseconds. So if you remember your graph, remember we mentioned that your inductor current will be rising as well as your inductor current will be rising. So let us just use this color. So your inductor current will be rising. All right, so if you look at your inductor current as well as your IR, your resistor current, it will be doing what? Rising. But for it to reach its maximum right here, which is going to be your 5 tau, then that maximum would actually be 25 microseconds here. Now, what if CSEC should get a little bit smart with you? And they should say, okay, ladies and gentlemen, tell me what is happening in this circuit at 30 microseconds. Then it's very easy. It is just a resistor alone that will be found in the circuit because that inductor no longer has an effect on your circuit. So that is why it's so important that you get to appreciate or understand, you know, the 5 time constant. So this is where our 25 is. Now we're going to be asking what is happening at 15 microseconds. So that is what we're going to be working out now, ladies and gentlemen. Now where is my eraser? Because I'm getting in this little mood now. So let us see if we can actually work out what is happening now at 15 microseconds. Now, if we're going to be calculating at 15 microseconds, and we're going to be asking, what do we want to find? Now, at 15 microseconds, let us say that we want to find our IL. What is our IL at 15 microseconds? Well, you remember earlier we said our IL is what? Rising. So IL will be equal to what? To find I, then it is V over R. And then we're going to be putting our what? Our rising factor, which is 1 minus e to the minus t upon tau. Now, all we need to do is actually fill in some stuff. Now, our V here is what? 20 volts. Our R is 20 kilo ohm. Or 20 times 10 to the 3. And then we're going to be putting our factor. 1 minus e. And remember our time? What is the time? The time that was given to us is what? 15 microseconds. So that is where we have a what? Minus 15 microseconds. And remember our time constant that we calculate earlier was what? 5 microseconds. Lovely. Nice that you're paying attention. 5 microseconds. So we have our 5 microseconds. And then we can close our bracket. Now, if we should just move on to this side of our board, then we're going to be reducing our circuit now. So if we should say IL is equal to what? 20 volts divided by 20 kiloohm. Then we will end up with what? 1 milliampere, or 1 times 10 to the negative 3 amperes. And then now if we're going to be simplifying what is in our bracket, 1 minus E, you notice we have here negative 15 microseconds divided by 5 microseconds. What did you calculate? 3 microseconds. Well, 3 seconds rather. So that will be what? E to the negative 3 seconds. Now, having done that, students, it is very important that you know how to put this in your what? Calculator. Very, very, very important. Now, having done that, 1 times 10 to the negative 3 amperes, and then 1 minus e to the negative 3 seconds, then what we're going to be calculating is that we will end up with our circuit having 0.95 milliamperes. So this is how we actually go about using our rising factor. And we're just going to be putting our falling factor on the board because we're wrapping up. So VL, you know that VL is actually falling. So our falling factor, you know, if we want to calculate VL at 15 microseconds, then we know that our total supply voltage is what? What we need right there, and then it will simply be e to the minus t upon tau. So that will be what? 20 e to the minus 15 upon 5, what is equal to 20 volts, e to the negative 3, and that will work out to 1 volt. That is what it will work out to, 1 volt. So we really appreciate the time and your energy. We're going to hand over to Mr. Green.
All right, guys, that's all today for CSEC Industrial Education, CSEC and Cape Electrical.